The objectives of this topic are decide whether an ordered pair is a solution of a linear system, solve linear systems by substitution, solve linear systems by addition, identify systems that do not have exactly one ordered pair solution, and solve problems using systems of linear equations. All equations in the form ax plus by equals c are straight lines when graphed. Two such equations are called a system of linear equations, or a linear system. A solution to a system of linear equations in two variables is an ordered pair that satisfies both equations in the system. A linear system that has at least one solution is called a consistent system. A linear system with no solution is called an inconsistent system. Two x minus 3y equals -4 and 2x plus y equals 4 make up this system of equations that we're going to consider here. We want to determine if the ordered pair 1, 2 is a solution of this system. Now, we know how to check if an ordered pair is a solution to an equation. We just plug it in and see if it holds. If it's true, it's a solution. If it's not true, it is not a solution. For it to be a solution to a system, it doesn't just have to work in one, it has to work in both. So we take 1, 2, and we plug in 1 for x and 2 for y. Into the first equation, we get 2 minus 6 is -4. That checks. So it would be a solution to the first equation. Now we need to check and see if it is a solution to the second equation. Plug in 1 for x, plug in 2 for y. We get 2 plus 2 equals 4. That is also true. So the ordered pair 1, 2 satisfies both equations and is a solution of the system. Determine if the ordered pair 7, 6 is a solution of the system. So we do the same thing. We're going to plug 7 in for x. We're going to plug 6 in for y. We get 14 minus 18. That is, in fact, -4. It is a solution to the first equation. We're going to take the second equation. We're going to plug in 7 for x and 6 for y. We get 14 plus 6 equals 4. Well, that is definitely false. Since the ordered pair 7, 6 fails to satisfy both equations, it is not a solution to the system. Now we can solve systems by 3 different main methods. One of those methods is substitution. With substitution, you're going to solve either of the equations for one of the variables. Sometimes we get equations that are already in the form x equals blah, 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 or y equals blah, blah, blah. And if that's true, then we can just skip this step. But otherwise, we're going to solve for x or we're going to solve for y. Then we're going to take that expression and plug it into the other equation for that solved variable. This is going to result in an equation that only has one variable in it. We solve for that one variable, and then we back substitute into one of the original equations to find the other variable. And then, just as with equations, we can check solutions in both of the system's given equations to make sure that we have found a solution. So solve by substitution, we have 3x plus 2y equals 4 and 2x plus y equals 1. Notice that that second equation has that y hanging out all by itself. It's in dangerous territory. We're going to isolate it from the rest of the equation by subtracting 2x from both sides. We've rewritten it, y equals negative 2x plus 1. We got that by subtracting 2x from both sides. Now we have an expression for y. We got it from the second equation, so let's plug it into the first equation. 3x plus 2y equals 4. But y is negative 2x plus 1. So now we have an equation that is all x. Let's solve for x. Distribute the 2. 2 times negative 2x is negative 4x. 2 times 1 is 2. And then 3x minus 4x gives us negative 1x, or negative x. Negative x plus 2 equals 4. We want to get the x by itself, so we want to get the negative x by itself. We want to get rid of adding 2. We do that by subtracting 2. Whatever we do to one side, we do to the other. Subtract 2 from both sides, we get negative x equals 2. That means x equals negative 2. So I'd been saying negative x, but we know that really what I mean is the opposite of x. So if the opposite of x is 2, then x equals the opposite of 2, negative 2. We're not done, though. We've only found x. So we're going to take that x equals negative 2, and we're going to back substitute it into one of the original equations. Here we have 3x plus 2y equals 4. Plug in that negative 2 for x. That gives us negative 6 plus 2y equals 4. Add 6 to both sides, 2y equals 10. Divide both sides by 2, and we get y equals 5. Thus, a proposed solution is negative 2, 5. A check will show that the ordered pair satisfies both equations. I leave that as an exercise to you. The solution set is negative 2, 5. So if you want to go back and show that negative 2, 5 works in both of the original equations, feel free to do so as some extra work. I said that there were 3 methods of solving linear systems. The first was substitution. The second is addition, also known as elimination. So for this one, we want them both in the form ax plus by equals c. The x and the y on one side, the constant on the other side. Then we want to make it so that the sum of the x coefficients or the sum of the y coefficients is 0. Sometimes this naturally happens. Other times we need to multiply one or both of the equations by appropriate numbers to get that to be the case. You'll see what I mean by this when we do our example. But then we're going to add the 2 equations. And since the sum of one of the coefficients was 0, that's going to get rid of one of the variables. The sum is going to be an equation in just one variable, which we will solve for, and then back substitute. So eventually it's just like substitution. This is just a different way of finding our first variable that we back substitute to get the other variable. And of course, we can check. So let's solve by addition. 4x plus 5y equals 3, and 2x minus 3y equals 7. Well, notice if we added these together, we would get 6x plus 2y equals 10. That doesn't do us a lot of good, though, because we can't solve that for x and just get a number, and we can't solve that for y and just get a number. We're still going to have the other variable. We want to eliminate one of the variables. Well, if we multiplied that second equation by -2, then instead of 2x, we would have a -4x. And that 4x plus the -4x would make the x's go away, giving us an added equation just in terms of y. So that's what we're going to do here. We're going to multiply the second equation by -2. And that's both sides. We're distributing, and it's on both sides. So -2 times 2x is -4x. -2 times -3y is +6y. +7 times -2 is -14. Now, when we add these two equations together, we get 11y equals -11, which we can quickly solve for y by dividing both sides by 11. We get y equals -1. We're going to take that y equals -1. We're going to back substitute it into one of the original equations. Here we have 4x plus 5y equals 3. Plugging in -1 for y, we get 4x minus 5 equals 3. Add 5 to both sides to get 4x equals 8. Divide both sides by 4 to get x equals 2. Our proposed solution, therefore, is 2, -1. And if you check, you will be able to bump that up from proposed solution to confirmed solution. The solution set is just the point 2, -1. X is 2, y is -1. Now, I said there were 3 ways of solving. The third way, which is actually technically the first way, is by graphing them both. For it to be a solution of both equations, it has to be a point that lies on both lines. That point will be the point of intersection. So the other way of solving a system of equations is to graph both of the lines and see where they intersect. Now we can see normally, most of the time, we're going to get exactly one solution. We'll have a line going one direction, a line going another direction, and they'll intersect at exactly one point. There will be one solution. But sometimes the two lines won't intersect at all. If they're parallel lines, then there's no solution. And sometimes they'll both be exactly the same line, in which case there's infinite solutions. The lines intersect everywhere. So let's go ahead and solve this system. You'll see how this connects in just a second. Spoilers at the top of the screen. We can solve this by elimination, by addition, by multiplying the first equation by 2. We multiply the first equation by 2, that'll turn that 5x into a 10x. The 10x minus 10x is going to give us 0 x's. The x will go away. So we multiply the first equation by 2, and we get 10x minus 4y equals 8. And when we go to add, something happens. Not only did the x's go away, but the y's went away as well, leaving us with just 0 on the left. On the right, we still added 8 plus 7, and we got 15. So we ended up with the statement 0 equals 15. This is false, which means there's no solution. If there's no solution, the system is inconsistent. What does that mean graphically? It means we had parallel lines. If there's no solution, that means the lines didn't intersect. That means we're in that case with the parallel lines. The solution set is the empty set. Once again, that means we have parallel lines. So what do you suppose we're going to do an example of now, huh? Once again, spoilers at the top of the screen. We want to solve x equals 4y minus 8 and 5x minus 20y equals negative 40. That system of equations. Well, x is already by itself. It says x equals. This is basically screaming, use substitution. So let's do that. If x equals 4y minus 8, then we plug 4y minus 8 in for x in the other equation. Distribute to get rid of the parentheses, 20y minus 40 minus 20y equals negative 40. 20y minus 20y cancel each other out. Negative 40 equals negative 40. This is a true statement. Whether that true statement is negative 40 equals negative 40, or if you add 40 to both sides for some reason to get 0 equals 0. True statements. Because it's always true, that means we have infinitely many solutions. That means these were actually the same line. If we wanted a solution set, the set would be the set of all points x, y such that one equation, or the set of all points x, y such that the other equation. So such that x equals 4y minus 8, or such that 5x minus 20y equals negative 40. Any point that makes that true is a point that is a solution, aka every point on that line, one form of it or the other. Let's look at revenue and cost functions. A company produces and sells X units of a product. The revenue function, R of X, would be the price per unit sold times X. The price times how many of them you sold. That's the revenue. That's how much money you've made, that you've brought in. That is different from profit. Profit, you have to take into account your costs. So we need to know the cost function. The cost function C of X would be our fixed cost, what we'd pay no matter how many we sold or made, plus the cost per unit produced times how many is produced. So the revenue, how much you bring in, is the selling price times how many you sold. The cost function is your fixed cost plus your variable cost. Your fixed cost plus how much per unit times the number of units. Revenue is money in, cost is money out. The point of intersection of the graphs of these two functions is called the break-even point. So a company that manufactures running shoes has a fixed cost of $300,000. Additionally, it costs $30 to produce each pair of shoes. They are sold at $80 per pair. Write the cost function C of producing X pairs of running shoes. Well, that's our fixed costs, our $300,000, plus our variable costs, plus $30 times how many we make. So 300,000 plus 30x is the cost function. The revenue function, money in. We're selling them at $80 per pair. That's 80 times x. The revenue function is 80x. So if we find where these intersect, in other words, if we solve the system of these two equations, we'll get the break-even point. C of x and R of x are both just y. Remember, y equals f of x. And if they're both equal to y, that means they're both equal to each other. So set them equal to each other. 300,000 plus 30x equals 80x. Subtract 30x from both sides. 300,000 equals 50x. Divide both sides by 50. We get x equals 6,000. We're not done. Y equals 80 times x, which means y equals 80 times 6,000. Y equals 480,000. So the break-even point is 6,480,000. What does that mean? Well, it means that the company will break even if it produces and sells 6,000 pairs of running shoes. At this level, the money in is equal to the money out. The revenue is equal to the cost. That revenue, that cost is $480,000. And that's it for this topic. When we talk about a linear system of equations, we're talking about two equations with the same solution, two variables. We're going to look at three variables in a little bit. So let's say we had a graph. And the first equation has some graph like this. Call that line 1. The second, we'll call this line 2. So here, these graphs intersect at exactly one point, some point x, y. We say that this system is consistent and the equations are independent. We also have the possibility that our two lines are parallel. In this case, we would say the system is inconsistent
and independent. Don't worry, I'm going to go back through these terms and help us make sense of them in just a minute. We also have the case where line 1 and line 2 are exactly the same line. Maybe we have two different equations that work out to the same line. We call this consistent and dependent. So, consistent, inconsistent, dependent, independent, what do we mean by this? Well, consistency, whether it's consistent or inconsistent, that is whether there is a solution or not. So this first example where the graphs intersect at one point, there is a single solution. There is a solution though, so it is consistent. Since the lines are different lines, they're independent. Different lines are going to be independent. The same line would be dependent. So come down here, the parallel line example. If two lines are parallel, they never intersect. If they don't intersect, there's no solution. If there's no solution, then it is inconsistent. They are still different lines though, so the lines are independent of each other. But then where we have the same line, well, all points on line 1 are also all points on line 2. So there are infinitely many solutions. And apologies if there should be an E in there. I'm not a spelling guy. I'm a math guy. I do know you could also just say infinite number of solutions. I know there's an E on that. I don't fall into that trap. But since there is at least one solution, that makes it consistent. But since the lines are the same line, they are dependent. The equations of the lines are dependent on each other. They are the same line. So we're going to come back to these vocab words. We're going to use them, consistent, inconsistent, dependent, independent, throughout this lesson. Keep that within reach. Now, graphically is no way to solve every equation. If you have a graphing calculator, it's a nice quick way. But for the purposes of our exploration of systems of linear equations, we're going to deal with the substitution method and the elimination method. So looking at example 1, we see something that we could use the substitution method on. We have the system 3x plus 2y equals 11, and negative x plus y equals 3. If we thought about this graphically, if we graphed this line and we graphed this line, wherever they intersect would be the solution for x and y. Sometimes you'll see a system of equations with a left brace, just showing that these are together. If we have two unknowns, we need to have two equations. If it was x, y, and z, we would have needed three equations to be able to solve. The solution we find is going to work in both. So it's not enough to find an x and y so that negative x plus y is 3. We're also finding that same x and y so that also 3x plus 2y is 11. This is called a simultaneous solution. So substitution is exactly what it sounds like. We're going to take something and substitute it somewhere else. We either want to get x equals something or y equals something. This is a good one for substitution because here we have an equation where the x and the y are by themselves. It would be really easy to solve for one. In fact, here's our positive y. If negative x plus y equals 3, then y equals 3 plus x. We're going to take that expression for y and plug it in the other equation. So instead of 3x plus 2y equals 11, for y, we're going to use that expression 3 plus x. So now 3x plus 6 plus 2x equals 11, which means 5x plus 6 equals 11. 5x equals 5. So we get x equals 1. We're not done though because we need x and y. We have x equals 1. We don't know what y is yet. But wait, y is 3 plus x. X is 1. So y equals 3 plus 1, which means y equals 4. So our solution is x equals 1, y equals 4. We could also express that as the ordered pair 1, 4. Remember, if you do an ordered pair, order matters, x then y. So that's the substitution method. We also have the elimination method. Some rules we have for elimination. We can interchange any two equations. We can just switch them around. We can multiply or divide any equation by some non-zero real number, if it's helpful. And we can replace any equation of the system by the sum of that equation and a multiple of another equation in the system. So that's the words. It's not really as complicated as it sounds. In example 2, we have the system 3x minus 4y equals 1 and 2x plus 3y equals 12. The elimination method is also called the multiplication addition method in some places. And that's because literally to do this, you're going to multiply and add in order to, wait for it, eliminate one of the variables. So if we added this down right now, we would get 5x minus y equals 13. We want to find two equations that we can add down, and one of them, one of the variables would go away. So let's say here with our y's, one of them's negative, one of them's positive. We're already off to a good start. What's the least common multiple of 4 and 3? 12. Well, what do we need to multiply 4 by to get 12? 3. What do we have to multiply 3 by to get 12? 4. Since one was negative and one was positive already, we're going to keep it positive 3, positive 4. We should end up with a negative 12y and a positive 12y, which will cancel each other out. When we multiply through, our new two equations are 9x minus 12y equals 3, and 8x plus 12y equals 12 times 4 is 48. Now, let's add down. 9x plus 8x is 17x. Negative 12y plus 12y cancels. 3 plus 48 is 51. Divide both sides by 17, and we get x equals 3. We're going to take that x equals 3, plug it into either of the two original equations, and notice either way, whether we're doing 3x minus 4y equals 1, or 2x plus 3y equals 12, when we plug in three for x, nine minus 4y equals 1, which means negative 4y equals negative 8, which means y equals positive 2. Or if you did the other equation, 6 plus 3y equals 12, so 3y equals 6, so y equals 2. Either way, you're going to get y equals 2. Pair that with your x equals 3. Our answer is 3, 2. You could always check, put them x and y into both original equations. As long as both equations check out, you know you're right. Now, let's look at some special systems. Example 3 says solving an inconsistent system. What did inconsistent mean? Inconsistent meant that there is no solution. If we graphed it, it would be parallel lines that never intersect. We have 3x minus 2y equals 4, and negative 6x plus 4y equals 7. That is our system. Here, we can choose to eliminate the x's or the y's. Positive, negative, negative, positive, so we'll choose a positive number either way. The signs will already be different. Notice, if you multiply this first one by 2, it gives us 6x plus 4y equals 8. And if we leave the second one alone, or sorry, minus 4y here. It should have been minus 4y on the top. If we leave the second one alone and add down, the x's cancel, the y's cancel, we get 0 equals 15, which is not true. So we get no solution. This is an inconsistent system because there is no solution. But we did not get the same line. They are not the same line. That's going to be the other type of special system. An example 4, solving a system with infinitely many solutions. (8x minus 2y equals negative 4. And negative 4x plus y equals 2. Positive, negative, negative, positive. So the signs will already be different from one equation to the other. We don't have to worry about picking a positive number and a negative number. Let's multiply the second equation by 2. That'll give us an 8 there, a 2 there, which will enable us to get rid of either variable. So this is going to be a special system because of the fact that both variables go away. But you'll see now the difference from the last one. Negative 8x plus 2y equals positive 4. Not only do we get 0 on the left, we get 0 on the right, which is a true statement. We have an identity. If it's always true, there are infinite, yeah, I think there's an E in there. Infinitely, unless there's not, many solutions. Why don't I just say all real numbers? Well, in this case, all real numbers would not be an accurate description. You can't put any number in for x and any number in for y and have it be a solution. There's infinitely many solutions of the form 8x minus 2y equals negative 4. You can pick a value for x and solve for y, and that will be a solution to the system. There are infinitely many solutions. So how do we describe infinitely many solutions? Well, remember that was where they are the same line. Notice only things on that line will be a solution, not something out there or something over here. Since there is an answer, it is consistent. Since it's the same line, It is dependent. As opposed to this one, which would graph as parallel lines, inconsistent and independent. Here we get a true statement, and that one we got a false statement. In both of them, though, both variables went away. We can see here this is the same line, because one of those rules for the elimination method was multiply or divide any equation of the system by a non-zero real number. So when we see this, we could have divided both sides of this by 2, by -2, which would give us exactly -4x plus y equals 2. We could have seen right there, they are the same equation. Can't do that here. There's no way of making the left side the same and having the right side be the same.
Okay, so we're going to go through and review systems one more time. And then I'm going to show you a word problem where we can actually use the concept of a system of equations to solve the word problem. So first, let's take the system y equals -2x minus 2 and 5x plus 5y equals 0. And let's solve this using the method of substitution. We would use substitution because it's very clear here that the variable y can be represented by -2x minus 2. So we're going to take that and plug it in for y in the second equation. So 5x plus 5y becomes 5x plus 5 -2x minus 2 equals 0. Distribute 5x minus 10x minus 10 equals 0. 5x minus 10x is -5x minus 10 equals 0. I need more room. I'm going to move it over here. -5x minus 10 equals 0. Add 10 to both sides. -5x equals 10. Divide both sides by -5. X equals -2. We're not done. We have to take our x equals -2 and solve for y. Y equals -2x minus 2. That means y equals -2 times -2 minus 2. Y equals -2 times -2 is +4 minus 2. Y equals 2. So our answer is going to be the ordered pair where x is -2 and y is 2. Another system of equations. This time our first equation is 4x minus 3y equals 10. 3x plus 4y equals -5 will be the second equation. Let's solve this one using the addition method. Well, we see this second term here. One of them is minus, one of them is plus. If only they were the same number, they would cancel away. Like if it was 3 and 3 and 4 and 4, we can't make that happen. What we can do is multiply that 3 up into a 12 and multiply that 4 up into a 12. We can accomplish that by multiplying the first equation times 4 and the second equation times 3. First equation becomes 16x minus 12y equals 40. Second equation becomes 9x plus 12y equals negative 15. And when we add them together, the y's are now gone. Minus 12y plus 12y cancel away. 16 plus 9 is 25. So 25x equals 40 minus 15. That's positive 25. We have 25x equals 25. Divide both sides by 25. We get x equals 1, but we're not done. We need to get y as well. So we pick one of the two equations that we started with. I'll just take 4x minus 3y equals 10, and x equals 1. 4 times 1 minus 3y equals 10. We're going to solve for y. 4 minus 3y equals 10. Subtract 4 from both sides. Minus 3y equals positive 6. And if we divide both sides by negative 3, we get y equals negative 2. So our answer is the ordered pair where x is 1 and y is negative 2. Camille and Sasha each make an ice cream sundae. Camille gets 1 scoop of cherry ice cream and 3 scoops of mint chocolate chunk ice cream for a total of 63 grams of fat. Sasha has 3 scoops of cherry ice cream and 2 scoops of mint chocolate chunk ice cream for a total of 84 grams of fat. How many grams of fat does 1 scoop of each type of ice cream have? With this information, we are able to answer that question. And we're able to answer it by first setting up a system of equations. Let's let C stand for cherry, and let's let M stand for mint chocolate chunk. And C and M are going to stand for the grams of fat in each of those. C for cherry, M for mint chocolate chunk. Let's read this again, starting with Camille. Let's make an equation for Camille. Camille gets 1 scoop of cherry and 3 scoops of mint chocolate chunk for a total of 63 grams of fat. So see what I did there? 1 cherry plus 3 mint has 63. Now let's do the same with Sasha. Sasha has 3 scoops of cherry and 2 scoops of mint for a total of 84. Now, if we solve for C and M, we'll get the grams of fat in 1 scoop of cherry and 1 scoop of mint chocolate chunk. Because this C is by itself, I'm going to go ahead and change C plus 3M equals 63 into C equals 63 minus 3m. And I'm going to take that C and I'm going to plug it into the second one. So I'm going to use substitution, but you could also do addition. You could multiply the top one by -3. Then you'd have a -3c and a 3c. Things would cancel. You can go from there. You'll get the same answer no matter how you solve it. You just have to be able to solve it. So if c is 63 minus 3m, then we have 3 times 63 minus 3m plus 2m equals 84. 3c plus 2m is 84. C is 63 minus 3m. And we got that by solving the first one for C. 3 times 63, that's 189 minus 9m plus 2m equals 84. 189 -9 plus 2 is -7m equals 84. Subtract 189 from both sides. That's going to give me -7m equals -105. If I divide both sides by -7, so -7m equals -105. Whoops. Divide both sides by -7. I get m is positive 15. What does that mean? That means that the mint chocolate chunk has 15 grams of fat per serving. Plug that in here. C equals 63 minus 3m. C equals 63 minus 3 times 15. C equals 63 minus 45. C equals 18. So this information the cherry has 18 grams of fat per serving. The mint chocolate chunk has 15 grams of fat per serving. The objectives of this topic: verify the solution of a system of linear equations in 3 variables, solve systems of linear equations in 3 variables, solve problems using systems in 3 variables. So in general, any equation of the form ax plus by plus cz equals d, where a, b, c, and d are real numbers such that a, b, and c are not all 0, is a linear equation in 3 variables, x, y, and z. So this is just expanding what we did with 2 variables to 3 variables. Instead of just x and y on one side with the constant on the other, we have x, y, and now z on one side and our constant on the other. But just like 2 variables, a solution is an ordered triple now of real numbers that satisfies all equations of the system. The solution set is the set of all its solutions. So let's just jump right in. Show that the ordered triple -1, -4, 5 is a solution of this system. X minus 2y plus 3z equals 22, 2x minus 3y minus z equals 5, and 3x plus y minus 5z equals -32. We have to plug -1 in for x, -4 in for y, and 5 into z for each of the three equations. We almost hope that it's not a solution, because that means maybe the first one or the second one won't be true, and then we don't have to go any further. So let's make our substitutions. Let's go ahead and multiply the -2 times the -4 to get a +8, the 3 times the 5 to get a +15, -1 plus 8 plus 15. That would be 7 plus 15, which is 22, equals 22. That one's true. Unfortunately, we need to move on to the second equation. Let's do it again. Plug in x, y, and z, -1, -4, and 5. That's going to be -2 plus 12 minus 5 equals 5. It's -7 plus 12. That's 5. 5 equals 5. That one's true. Oh, this one might just be a solution. Let's move on to the third equation. 3x plus y minus 5z equals -32. Make our substitutions. Plug in that -1, that -4, and that +5. We get -3 minus 4 minus 25 equals -32. That's -7 minus 25. That's -32 equals -32. That is true. It's satisfied all three equations, which means that the ordered triple -1, -4, 5 is a solution of the system. So checking with three variables, not so different than checking with two variables. The difference is the time that you spend doing it. With two variables, you were checking two substitutions and two equations. With three variables, you're checking three substitutions in three equations. So instead of doing 4 things, you're doing 9 things. Now, how do we solve systems of linear equations in three variables? Well, the goal is to eliminate variables. We know how to solve systems in two variables. So if we can give ourselves a system in two variables, we can go ahead and solve that. Once we find those two variables, back substitute into one of the equations, we find the third. So we're going to start by reducing to two equations in two variables, accomplishing this by taking two different pairs of equations and then using the addition method to eliminate the same variable from both pairs. We'll use the resulting system of two equations to find two of the variables, back substitute, and find the third. Then, of course, we can check. Let's get at it. X plus 4y minus z equals 20. 3x plus 2y plus z equals 8. 2x minus 3y plus 2z equals -16. I miss my favorite problem. Imagine a system of equations where you had x, y, and z in the first one, you had y and z in the second one, and the third one was z equals a number that tells you right what to plug into the y and z to solve for y, which tells you right what to plug into the x, y, and z for y and z. You get x, y, and z by back substituting 3 times and you're done. That's the easiest type of system of 3 equations that's out there. An x, y, z, y, z, z. Or an x, y, z, x, y, x. But no, here we have X, Y, and Z in all 3 of them. We're sad because this is going to be a lot of work. But as long as we tackle it in an organized fashion, we should be able to manage. So we want to use elimination twice on 2 different pairs to eliminate the same variable in both places. Let's go ahead and eliminate Z. This is a very good first move to make because we notice in equation 1, we have minus Z. In equation 2, we have plus Z. Right away, if we add 1 and 2 together, we're going to eliminate the Z's. We'll have 2 equations that only have X and Y. Then we're halfway there. Well, halfway to halfway there. We're almost there. Almost. So add equations 1 and 2. We get 4x plus 6y equals 28. Now, we want to take care of equations 1 and 3. In order to do that, to get rid of the z, since we have a plus 2z in the third equation and a minus z in the first, we can multiply equation 1 by 2, which will give us a minus 2z here, which will cancel with the plus 2z. We'll be good to go. So multiply equation 1 by 2, 2x plus 8y minus 2z equals 40. Add, we get 4x plus 5y equals 24. That's 2 equations with 2 unknowns, just x and y in both. We know what to do there. Make it a system of equations and solve. If we just change the signs on the second equation, multiply it by -1, that'll give us a -4x to go along with our 4x on top. Changes all the signs, plus 5y to minus 5y, plus 24 to minus 24. But when we add, we get y equals 4. Right off the bat, no division necessary because of that 6y minus 5y. Now that we know that y equals 4, we plug it into one of these equations. We have 4x plus 6y equals 28 here. Plug the 4 in for y. 4x plus 24 equals 28. Subtract 24 from both sides. 4x equals 4. Divide both sides by 4. X equals 1. Now we have x equals 1. We have y equals 4. Let's back substitute those into one of the originals. X plus 4y minus z equals 20. And actually, before I do this, I want to go back a little bit in time for a question you might have had here. Why did I add 1 and 3? Why did I change equation 1? Why didn't I do 2 and 3? We can do 2 and 3. I could have multiplied equation 2 by -2. And then that -2z in equation 2 would go with the 2z in equation 3. We would still get a system that gives us x equals 1 and y equals 4. And we just have to think about the fact that a solution is a solution to understand why that would be the case. Because this x equals 1 and this y equals 4 has to be part of the satisfaction of all three of the original equations. That's also why it doesn't matter which of the three we pick to plug our x and our y into. We just happen to pick x plus 4y minus z equals 20 here. But we could have done any of the three, plugged in the x and the y we found, and we would get the same z. That z is -3. Plug in our 1 for x and our 4 for y. That's 1 plus 16 minus z. That's 17 minus z. Equals 20. Subtract 17 from both sides. The opposite of z equals 3. So z equals the opposite of 3, -3. Our proposed solution is 1, 4, -3. If you want to go ahead and prove what I just said about a solution, you can go ahead and substitute that ordered triple into all three of the original equations. You will find that it does satisfy all three of them. Thus, it is a solution. The solution set is that ordered triple, 1, 4, -3.